So let's finish our topic on computer architecture today, okay? So then just a small subpart for logic, then your syllabus is over, okay? Right, so last time we started discussing computer architecture. We discussed stack architecture, stack process architecture, and accumulator process architecture. Of course, those are these days, early days, those were the main architectures, but these days, those are some supportive architectures only. So today we look at the modern process architecture, that is GP, General Purpose Registry Architecture. Okay, General Purpose Register Architecture. So let's start from that point, because we already done stack and accumulator architecture. So remember, stack and accumulator is more towards processing complex expressions, arithmetic or logic expressions like x plus y into z plus z minus 1, 5 or something like that. What is the best way to keep processing this? But modern computers are no longer just calculators or simple data processing devices. So the modern computers are more general devices where we can do word processing or text processing, image, audio, video, and also very complicated programs, accounting systems, inventory management systems, transaction processing. So doing set of things as a program. So that is where general purpose registry architecture evolved, and general purpose registry architecture. So general purpose registry architecture is more suitable for running programs, set of instructions. But again, those set of instructions may include expressions, arithmetic and logical expressions. So that is why still we use accumulate and stack architecture to process these individual statements. But overall, running your programs, so the overall architecture is now general purpose registry architecture, whether it's a laptop, desktop, or even your smartphone. Okay, so therefore it's an overall architecture. Okay, still other architectures support evaluating the expressions. Right, I will get back to register, and okay, I will explain the two approaches also. So when it comes to general purpose registry architecture, there are two sub approaches. One approach is called register approach. Other one is called register memory. Another name for register is load store. Okay. So the difference is in register approach, always we load data and instructions to the registries and then execute from there. Okay. Always, especially data. Anyway, instructions, anyway, we need to load it to the registries. But data, first we load it to the registries, and from registries you take it to the ALU. That is called register approach. In register memory approach, okay, in register memory approach, some data you can keep it in the registry. At the same time, some data you can directly take it from memory to the ALU. Okay. So then you call it register memory. It's a mixed approach. But this approach is not much used these days. Actually, not at all used these days. Because these days we always, processors always load data into registries. And from registries only, data is taken to the ALU and processed. And again, results are written to the registries. And later, from registries, data is written back to the memory. So that is a modern approach. But early days, ALU used to directly fetch data from memory and writing directly to the memory. Okay, that is a difference between register versus register memory. But modern computers are pretty much register. Okay, so this is an example. You will gradually get to know these kind of statements. These are assembly code. Assembly code is low-level programming, referring to the computer architecture and hardware and getting things processed. Say simply, I want to execute this statement. Say A and B are memory locations. Values in memory location A, values in memory location B. And I want to add those two numbers, assume those are numbers, and put the results into memory address C. Of course, memory can't do addition. So that is why we need the support of ALU or processor. So if you go for register approach, so all these data first you need to load to registries. So we call them general purpose registries. That is why we call this architecture GPR architecture. General purpose registry architecture. Okay. So you can assume that you have registries like registry 1, registry 2, registry 3. Usually those are numbers, hexadecimal numbers. What we are writing is not actually assembly code. This is pseudo assembly code. Pseudo assembly code means assembly code, but not real assembly code, because real assembly code has additional complexity. So real assembly code must be learned or used by computer engineers, electronic engineers, digital electronic engineers, because that is their main subject. But when we do computer science, software development, IT, our task is understand how the computer will process. Our task is not designing computer processors. So therefore, pseudo assembly is good enough for us. Otherwise, it will take more time for us to learn real assembly and write programs. So we write real Java programs, PHP programs, Node.js programs. So that is our task. So therefore, let's stick with pseudo assembly, because we don't want to spend our time more on these low-level programming. But we must know what's happening inside the computer. That is required for our confidence. That is why we have the computer architecture subject. Right. So this is sort of a pseudo assembly code. Real code is very close to this, but it has additional complexities like real memory addresses and so on. Right. So we load the value in memory address A to register 1. So this is my memory. The memory addresses are called A, B, C, D. Registries are called R1, R2, R3. Of course, memory is in RAM. Registries are in the ALU. So you load the value in memory address A to register 1. So this instruction will be first executed. Then load the value in memory address B to register 2. Now those two values are in register 1 and register 2. Now we can ask processor, add the values in register 1 and register 2 and write the result back to register 3. Okay. Now register 3 has after this third statement is executed, register 3 has the A plus B, or the values in memory address A and B. Now, of course, we need to write it back to the memory, because other application input-output devices can refer only to the memory, not to the registry. Therefore, we can say store the value in register 3 into memory address C, so that other devices can access the memory address C. So this is how you add two numbers at very low level, not binary code, assembly code, second generation code. So that this is how computer engineers, programmers used to write programs in 1950s and 60s. And even today, when you write our Python program, Java program, when you compile, so it generates this kind of a program first. At runtime, this program is further converted into set of ones and zeros. So that is every statement has a binary number. These become the registry numbers and memory addresses. So therefore, it looks like set of ones and zeros, but that set of ones and zeros represent this kind of a statement. And this kind of a statement is generated by your like int x, y, z, x equal 10. So related to that, first it generates this kind of a code. Then at the execution time, it generates this kind of a code and execute. I gave you few. Remember, so far we saw a particular slide 2 times. Now I hope it make more sense to you. So this is your source code, Java, Python. This is intermediate assembly code, and this is the binary code corresponding to the assembly code which is executed. Okay. Okay, so that is if you go for register approach. Of course, modern computers use register approach. Okay, but if the computer use register memory approach, that means your assembly code can refer to memory addresses also. That means your ALU can, now here, always your ALU take inputs from registries. Okay? These are registries. And write the results to registries. So therefore, separate statements must load values to registries and write the results to the memory from registry. So this is loading, this is writing. And your processing statement only refer to registries. Okay. Right. That is register approach. If you go for register memory approach, your ALU can not only refer to the registries, it can directly get data from memory. But the results are usually written back to registries, or even it can be directly written to the memory as well. So it's a mixed mode. So that means ALU can get data from both registries and memories. Okay. So then you call it register memory approach. Of course, this approach is very rarely used. The main reason is accessing data from memory to the ALU take a lot of time compared to get it from registries. So that create delay, inefficiency. That is why we no longer use this approach. But anyway, because of historical reasons, you must know what is register memory approach is. Right? So this one, you load the value in memory address A to registry 1. So then add value in registry 1, that is the memory, earlier the value in memory A, and value in memory B. Now you are taking value from memory B, value from registry 1, because registry 1 already has the value for memory A, and write it to registry 3. Later, write the value in registry 3 back to the memory address C. So it's a mixed mode. Right? Your operational statement refer to both registries and memory addresses. That is what is meant by register memory approach. Okay. Of course, in the very early days, they were referring to memory. There was no concept called registries. Then intermediary like hybrid registry memory. And these days it's register because processing statements refer to registries. Okay. Right. Any questions? So I told you this is computer system subject. In computer system subject, you can't say I don't understand anything. No, you must have understood everything 100%. Whatever we have, put it into your slides, your syllabus, because this is formal science. So you can't say I have somewhat understood. How can you say like that? Of course, you can say that for chemistry, physics, biology, even I would say I have some understanding about chemistry. Even within the syllabus, still I have some understanding because I did my A level and I did chemistry. But again, even within the A-level syllabus, I have only some understanding. Okay. But you can't say that for formal science subjects. Within the syllabus, you must have 100% understanding. If not, you must accept that no, I don't, I have only 80%, 90%. So that is anyway, I will settle it maybe. But ideally, you should have understood 100%. So that is why I'm asking you to ask questions. Because if you are not very sure of something, there's a solution for that. There's an answer for that. But that is not the case when you learn chemistry, physics, biology. There may not be a perfect answer. So just because you don't understand it doesn't mean that others have not understood it. Yes, others may have understood it. Definitely. Okay. So ask from there. Ask from ChatGPT. Okay. So if you're still in doubt, right, go to ChatGPT. Of course, ChatGPT is not yet perfect, but it's getting more and more perfect. Right? Sudo assembly code refer to register memory architecture. Or maybe you can say simple code, simple program. Okay. Of course, still ChatGPT is also getting developed, but let's see. Okay, it's referred to the real lab addresses. You can see, not XY. I just make it easier for you. Okay, you can see this is real memory address to real registry number called R0. Right. So load the value in this memory address to registry 1. Then add the values in registry 0 and registry 1 and put it into registry 2. Then store the value in registry 2 into this memory address. So this is a different memory address. It's a hexadecimal memory address. Hold means stop the program. Okay. So this is also not the real assembly. But this code is little bit more realistic because it refers to the numbers rather than XY. Okay. So there are so many ways you can learn. Okay. So you can't say I don't understand. Right. So now you know what is register approach, register memory approach, and you know that mostly these days we use register approach. Right. So this is how general purpose registry architecture work for the modern computer process data or modern computer processor process data. So it keep executing what is known as fetch, decode, execute cycle. Fetch, decode, execute. Fetch, decode, execute. Fetch, decode, execute. So the first instruction, fetch, decode, execute. Second instruction is also fetch, decode, execute, and so on. So this is the big picture. This is your processor. This is your memory. This is your system bus. We have shown only data bus and address bus. Control bus is also there, but not shown for simplicity. Okay. So how does this work? So you remember your program is now in the memory. Program in the sense assembly code, compile code. Your data is also in the memory. Data related to this program. Okay. So this is your program. This is your data. For some other data will also be there. Other programs will also be there. OS will also be there. Now, so I'm explaining this at a high level, abstract level. So why I'm explaining at high abstract level? Because you guys are not learning computer engineering. That is why I'm explaining it high abstract level because your task is understand how the computer works. Right. So this is my program. it has set of assembly instructions now. So the first thing is, the first instruction is loaded to the instruction registry. So basically, these are the data registries. So the general purpose registries. So these registries, usually we have about 10, 20, 30, 40 registries in a computer. So these registries are used to store data. Okay. And this is where you keep your currently executing instruction. So we call that, it's a registry in ALU. We call it instruction registry. Instruction registry. So instructions are not kept in these general purpose registries. Instructions is only one instruction registry. Why? In a typical simple processor, only one instruction is executed at a time. So therefore, it's single registry. So this is another registry called program counter registry. So this registry is used to keep track of which instruction is currently being executed. So there is a memory address of the current instruction and sometimes next instruction. It depends on which part of the cycle you are in. So in general, program counter keep track of which instructions currently being executed. It's a registry. So these are also registries. This is a registry. This is also registry. So remember, we are going through fetch, decode, execute cycle. So once the instruction is fetched into the instruction registry and relevant data is assumed available in data registries, now your instruction is in which format? Assembly code, like load registry 1, memory 1, add registry 1 and registry 2 and put it into registry 3. Still, this is not machine code. So this is not the language of the computer. Language of the computer is set of ones and zeros. Your data is set of ones and zeros. Your instructions are also a set of ones and zeros because each instruction has a number. So therefore, your instruction, which is in assembly code, must be further processed. So that is done by decoder. So decoder will convert your assembly code into machine code for that instruction, right? Machine code. So once it is decoded only, it is machine readable or hardware readable and can be executed. So that is why it is fetch, get the instruction, decode, and then execute. Execute is done by the ALU. And the result is written back to registry or blah, blah, blah. And then the next instruction is fetch, decode, execute. Next instruction is fetch, decode, execute. How do you know what is the next instruction? Because program counter keep track of what is the current instruction. Right? So some of the instructions are processing instructions, like add R1, R2 and put it into R3. But some instructions are load instructions, load the value in memory, particular memory address to particular registry. Or store instructions, write a value in particular registry to a particular memory address. So your program consists of load statements, processing statements, and store statements. So that means not every instruction is doing some processing. Assembly code. No, some instructions, generated assembly code instructions, are loading data to the registry. Some instructions writing the value in registry to the memory. And some instructions do the processing. Then the values are taken from registry and written back to registry. Okay. Right. So I explain about registry. So these are general purpose registries, ALU, decoder, instruction register, program count. So then what is this? These are also two special registries in the processor. Memory address registry and memory data registry. Okay. So why do we need memory address registry? Or sometimes we call it memory address buffer, memory data buffer. I told you why do we need buffer? So whenever there are two components working at two different speeds, you need a buffer because these components are not sync. So therefore, when the processor want to load some value from memory or content from memory, it will write the memory address of that memory to the memory address registry. With it can be instruction, address of instruction or data. So it will keep it there. So then your memory will read that value through address bus because address bus is used to send memory addresses, and content of that address will be sent through data bus. And again, it will be kept in the memory data registry because memory and processor operates in two different speeds. So therefore, it will kept it there so that when processor is ready, it will take it. It will take it to the instruction registry if it is a instruction. It will load it to the general purpose registry if it is related to a data. Right. So here when we say data bus, sometimes you get confused. So data bus is basically taking the contents. So therefore, this data bus can take both data and instructions because data and instructions are both memory contents. So sometimes it's confusing. People just say data bus. So it should have been ideally content bus, memory content bus, because it can take the memory contents. So world is not perfect. Sometimes people loosely give names and these names become sort of a permanent. Therefore, don't think that this is only data. So same thing happens, right? When I ask students what is the purpose of memory, they say store data. But in reality, store data and programs. So similarly, when we say data bus, uh, it is not just you are taking the data or writing data. You take both data and instruction because memory. So this ideally should have been content bus name. Okay. Right. Any questions up to this point? At this level of abstraction. That is how you understand things. At different levels of abstraction, we understand perfectly. So that means we hide some additional technical details because we want to understand at a high level perfectly. That is the whole purpose of having these models and so on. But at the same time, don't think that this is not reality. This is getting closer to reality. Or it's like a picture is getting now somewhat getting clear, blur, and more getting clear and clear. Okay, so therefore, memory address registry is connected to the address bus. Memory data registry is connected to data bus. You can see here we have only one way arrow because we always send the memory addresses. But here it's two-way arrow because if it is a load statement, we are getting the data. If what we are executing is a store statement, you are writing data to the memory. So you can see you must pay attention to each and everything. Why this is like this? Why this is like this? You can see this is this way. This is this way. This way. This way. This way. Sometimes you read. Sometimes you write. Okay. Right. So that is how, at high level, you understand fetch, decode, execute cycle. Other than these, there are some other registries which we have not shown for simplicity, like status registries and so on, which are also referred to execute the statements because there can be exceptional situations. And also there's something called time sharing. Bit of program 1 is executed, then the program 2 is executed, then 3, and again back to A. So that gives additional complexities, and to handle that, you need extra registries and so on. But let's not look at those things at this level. Okay. Right. So I explain you what is the instruction registry is doing. It keep the currently executing instruction. Program counter is keeping track of current instruction or the next instruction address. Memory address registry is keeping the memory address of next instruction to be fetched. Okay. Or data to be fetched. Memory data registry or the memory data buffer keep the data to be written to the memory or memory data that we just got it from the memory. And general purpose registries are the data registries. Okay. So there's a small mistake here, so there should not be GPR separately here. It is just how to see this GPR here. So there should not be something for GPR separately here because this is a picture taken screenshot. It has some issues. Okay. So this should be just the registries. So the GPR registries. Okay. Let me hide this. Otherwise, you get confused. So there's a small break, but that is better than confusion. Okay. Right. So now you should be able to explain the fetch decode, right? Fetch cycle. Uh, at the beginning, the memory address of the first instruction is loaded here. That memory address is loaded to the memory address registry. That address is sent to the memory, and content of that memory, or that is the instruction, is sent from memory to the memory data registry. And when the processor is ready, that instruction is copied to the instruction registry. That is called fetch. Right? 1, 2, 3, 4. 1, 2, 3, 4 is part of the fetch. And of course, next time it will be having. Okay, so let's move on to the decode now. So decode is now instruction registry has the first instruction. So it is sent to the decoder because this instruction is not yet machine instruction, it is an assembly code. And the decoder converted it to machine code. Right? After decoder decode the code into machine code, your program counter can understand what is the next instruction. So therefore, it can update the program counter to point to the next memory address of the instruction of the next the next instruction's memory address. So before it is getting executed, program count is being updated after decoding. So that is why it is after 5 decode, 6 update the program count. Okay, so that is a decode part. And then you move on to the execution. So the instruction is executed. Actually, instruction is executed means your control, you need to send a control signal to the ALU to fetch the relevant data and conduct the relevant processing and write the result back. So all these things happens in the execute. That means now that instruction is executed. And your program counter already have the memory address of the next instruction. Now, again, you are going back to the fetch because your program count has, because after decoding, program count is already updated. So now you are going back to the fetch. This memory address is loaded to memory address registry. That address is sent to the memory. Memory send the content of that address to the memory data registry. If it is instruction, it is fetched to the IR. Okay, of course, if it is a data, it is fetched to the registry. But I am more interested about the processing. So then it is decoded. Program count is updated. That is a decode. Now that particular instruction is executed with the help of control unit and ALU, and the results written back to the registry. Now we are going back to the fetch. because PC is already updated, and this continues. This continues until this continues until three possibilities. One, all your program instructions are executed. So that means it has executed entire program. That means your program is finished. Until that, this fetch, decode, execute keep happening. Or else, user has decided to stop it. So then also, all of a sudden, this fetch, decode, execute cycle stop for that program because user has stopped it, closed the program. Maybe still it is while it is being run, user has closed it, stop it, terminate it. The third possibility is when this is being executed, fetch, decode, execute cycles, some runtime error happens. Error means it cannot continue. So then also the program will be terminated. So what are the three possibilities? Program is finished, user has closed it, due to fatal error, OS has decided to stop the program. So I'm doing this very slowly because I told you this is one of the most complicated things man has ever made. Right? So people used to say it is not rocket science, but the better word is it is not processor science, because the most complicated device man has ever made is computer processor. So now we try to understand that at abstract level. Okay. Any questions? Right. So now if you don't have any questions, so that means you are on track, okay, to understand, get the confidence. As a secondary results, pass the exams also. But your main objective is understand, get the confidence for your life, for your career. Right. So remember we discussed about assembly codes, second generation code. So second generation code can be written for stack architecture, accumulator architecture, or general purpose register architecture. Remember? So last week we discussed about stack architecture. So this is the generated code to execute statement like this. So this is converted to postfix and post. We using stack. You can say push S, push Y, multiply, push W, push U, multiply, add O. And if it is accumulate architecture, remember always we take one value from accumulator, other value from registry or memory, depending on your registry or memory you are using. So then the generated code is slightly different. The load A, add B, multiply C, add D. Because when we say load A and add B, it is B is added to A, and result is in now accumulate. When we multiply C, that result is multiplied by C. Yes. So this is slightly different code, but this is also assembly code. Assembly code referring to accumulate architecture. Right. So earlier we had something like push A. Now we have something like add B or load A. So that means load the value in memory address A to accumulator registry. But this is also accumulator. Add value in accumulator registry to B and bring back to the accumulator. This is stack architecture. Push A, push B. Stack architecture can have even something like mult. That means take two values from stack, multiply, and write the result back to stack. You don't need to say anything. You just say multiply. You can see depending on the architecture, your assembly code looks different. So therefore, when you read an assembly code, first you must ask what is the architecture. So then they will, if someone say, okay, I'm referring this assembly code is for stack, and now you can understand it, or he or she will say, okay, this is for accumulator. Okay. Or this is for general purpose registry. Sometimes by looking at it, you can guess it, but usually when someone give you a assembly code, he or she must specify this code is referring to this architecture, right? Right. So whatever the architecture, we don't care whether it's stack, accumulator, or general purpose registry. Assembly is assembly. Assembly code is assembly code. So let's look at some instruction formats in assembly code. Some instructions have just the operation code. Operation code means operation to be done. It just say add. So these kind of things you will see in stack architecture. When you say add, it means pop two values, add those values, and push the result or write the result back to the stack or push it. But you don't need to say all those things. You just say add. So that is why in stack architecture code, assembly code, you show that kind of assembly code. You can say just it says mult, just add, just sub. Okay. Sometimes operation code and memory address. Push the current value in as stack to the memory address or registry 20. That is the second format. That is operation code and operand. So you will see that those kind of things in stack and also accumulator. In accumulator, you can say something like load R1. That means load the value in register 1 or memory address 1 to the accumulator. So what is mean by this? This is also accumulator code. Add the value in accumulator to R2 and write the result back to accumulator. So therefore format is still the same. Operation code, operand. So you can see this can be found in stack and accumulator. Stack and accumulator. So third format is opcode and two operands. So those kind of instructions you will see only in GPR architecture that we discussed today. Say load the value in memory 1 to register 1. So this is your operation. These are the operand. This operand is referred to a registry address. This operand referred to a memory address. Load the value in memory address 2 to register 2. Add the value in register 1 and register 2 and write the result back to register 2. So if you have only, for add kind of operation, if you have only two operands, that means write the result back to the first register. Okay. So this is a store statement. Store the value in register 2 to memory address 3. So these are opcode, operand format. That format you find only in GPR. In GPR, you will see another format that is opcode, operand, especially for processing instructions. So sometimes we process two values and write the result to a different registry. So then you have three operands. So this means add values in register 1 and register 2 and write the result to register 2. Don't replace it to register 1. Because maybe later also you want this value in register 1. Right. Got it? So opcode only, opcode and operand, opcode and two operands, opcode and three operands. Some of these formats are used in only specific architectures only. Some formats used in multiple architectures. Remember we discussed pseudo assembly code, okay? So these are further processed into machine code. Right, anything, any questions? Because I'm finishing one subtopic and going to the, so usually I ask any questions when I finish, when we are done with the one subtopic. So that is instruction formats, assembly instruction formats. because our next subtopic is addressing formats, or addressing modes. Addressing modes. Okay. So as I told you, when you write your program or the assembly code, of course, when we write Java code, Python code, we don't refer to memory addresses. But when the assembly code, or when we write assembly code, or when the assembly code is generated, so that code refer to memory addresses. Okay. So there are different ways we can refer to memory addresses. We call them addressing modes. Right. So there are 4 addressing modes in assembly coding. First one is called immediate addressing mode, direct addressing mode, indirect addressing mode, and displacement addressing mode. So another name for displacement is index based or relative. So let's take one by one. So the first addressing mode is immediate. So actually immediate is not an addressing mode, but it's also referring to data. Therefore, we just call it addressing mode. So when you give an instruction, rather than memory address, if you are referring to the value itself, like a hard-coded value, we call it immediate addressing mode. Okay. For example, if I say add, say registry 1, registry 2, #10. So if this is R, say let's write something like add registry 3, registry 1, registry 2. So that means add the value in registry 1 and registry 2 and put it into registry 3. But let's assume, so rather than registry 2, here we have #8. So that means this addressing mode is immediate. So that means this is not a memory address or registry address. This is a data. So that means that add the value in registry 1 to number 8, value 8, and put it into the registry. So this is not registry or memory address, this is the value. So therefore, this is called immediate address mode. Or we say that for the second, third operand, we use immediate addressing mode. So the addressing mode can be vary for different formats, different operands. So these operands we are not using immediate, but for third operand, we use immediate. Okay. So this is add the value in registry 1 to 5 and take the value back to registry 1, the new value. Okay. So this is again pseudo assembly code. So therefore, in your pseudo assembly code, the convention we use is we use hash to denote that it is immediate. Or your question will say that assume that the second operand use immediate addressing mode, something like that. Okay, we'll do some past paper questions. Actually, we are going to do a lot of past paper questions at the end of this session today itself. Okay. So either you see that there's a hash or the questions say that for this particular operand, we use immediate addressing mode. Okay. So the next addressing mode, the second addressing mode is direct. Actually, it is the direct addressing mode we have been using everywhere so far. Okay, everywhere. In direct addressing mode, as the name says, you are referring to the memory address or registry address. Okay. For example, load the value 200 to registry 1. So this is direct. So when I say registry 1, I really mean registry 1. That means this is memory address 200, oh sorry, not the value 200, no hash. Say value in memory address 200, load it to registry address R1. Maybe the memory address 200 has 160 now. After this is executed, your registry 1 has 160. So therefore, this is direct memory address. This is direct registry address. So value in memory address 300. Say value in memory address 300 is 220. Load it to the registry address 2. So this is direct memory registry address. This is direct memory address. Then values in registry 1 and registry 2, add and store it to the registry 3. Again, we are using direct memory mode, addressing mode. Sorry, direct addressing mode. Store the value in registry 3 into memory address 400. Now the value result, that is 380, will be stored here. So everywhere we use direct memory address mode. Sometimes registry direct, sometimes memory direct. Okay. And this is most widely used addressing modes, especially in your exam questions. But anyway, they need to tell that what is the addressing mode. Okay. So now we move on to the indirect. Right, indirect. So as the name suggests, we are not directly telling the address. We indirectly tell the address. Right. So in this case, when you refer to address, actually that is not the address of the content. That is the address of the address. That is why we say indirect. So in your papers, because we consider pseudo assembly, usually it is mentioned inside bracket, but it is not a must. Most of the time, if it is indirect, your question will say, for this place, we use indirect addressing mode. Okay. Now let's assume this is a assembly code. Okay. So this says load the value in. So it's, if you simply say, it's something like load the value of registry 2 to registry 3. But that is it. This is direct, this is direct. But let's assume this is not direct. This is indirect. So this is direct, this is indirect. So then say registry 2 has some value. Say registry 3 maybe currently have some value, but we are not interested. Now you go to registry 2, it has a value, but remember, if this is direct, you load the value 918 to registry 3. But that is if this is direct. Now assume this is indirect. Okay. So then you go to registry 2. Registry 2 has a value, but that value is not the value. That value is the address, usually memory address. So then you go to this memory address. That is where you have the content. So in this case, it is 600. Now 600 is loaded to registry 3. So at the end, registry 3 will have 600. So that is if this operand use indirect address mode. Indirect. If this is direct, of course, 980 will be loaded to registry 3. But this is, if this is indirect, if you go to the 980 memory address and then load that value to registry 3. Okay. So that is registry indirect, because this registry is indirect mode. This registry contains indirect address. Usually when we say indirect, that address is a memory address, not a registry address. Usually one registry is not referring to another registry, but it can be your registry is referring to a memory address. Okay. Or it can be memory indirect. So if it is memory indirect, say this is load the value. If you just consider this as direct, load the value in memory address 1024 to registry 3. That is if both are direct. But assume this is direct, this is indirect, and this is a memory address, not a register number. So then you go to memory address 1024. If this is indirect, if it is direct, you load this value to registry. But if it is indirect, now look at what is this value. And that is your actual memory address. Now you go to this memory address and find the content and load that content to this registry. So therefore 800 will be loaded. So that is assuming that this is memory indirect mode. Okay. Memory indirect mode. So any question, anything not clear? Because you should be able to understand this 100%, not 99.9%. Okay. So indirect addressing modes means if it says that it is indirect, assume this is direct, this is indirect. Now you go to this memory address because it is indirect. Now this is not your data, this is your actual address. So now say assume this says 500. Now you go to the 500 and that is your data. Now load that data into registry, assuming this is direct. If this is direct, 500 will be loaded here. If it is indirect, 800 will be loaded here. There is a difference between direct and indirect. Okay. So indirect means your memory address or the registry address contains the address of the data, not the data. Immediate means it contains the data. Direct means it contains the address of the data. Indirect means it contains the address of that address of the data. Right? So it contains the address of the data. Indirect. This is the address of address that contains data. Yes. Data is this. Okay. Right. So now you're into the final addressing mode. So usually we call it displacement, but some people refer to it as index, some people refer to it as base, some people refer to it as relative. So therefore you never know which word will be used in the exam paper and also books. Displacement, index, base, relative. So just consider it's the same thing. This is very much similar to direct. So direct means your operand contains an address. But if the question says it is displacement or index or base or relative, that means there's another registry in the processor called base registry or displacement registry. I told you that the processor has some other registries as well, like status registries and so on. So this is another such registry in processor called displacement registry or index registry, okay, or base registry. Then when you refer to the address, you need to add the value in this registry to the address and then go and get it there. Then after you add this value in this direct registry or index registry or base registry, from that point onward, it is like the direct. Right? Direct means you go to that address and get the data. But you need to add these values, displacement value. Okay. So let's take an example. Let's assume that this is direct mode. This is direct. Question එක දෙනවා හරිය direct මොනවාද? And this is displacement or base or index. And assume this is the base registry value or index registry value. Now now assume this is the current values in the memory. Memory address 200-160, 300-220, and blah blah blah. Right. So this is what happens. You go to this memory, let's assume this is a memory address. Go to memory, because it says displacement, add the value in base registry or the index registry to this displacement value. So that means this value, you don't directly go to 150. You go to 150 plus 250. 150 plus 250 is 0, 0, 400. So therefore, don't go to 150, rather go to 400. Right, 400. And that value you need to load to register 1. So assume that that value is, say, 900. So now 900 is loaded to register 1 because 150 plus 250 is 400. So the value in that registry is loaded to, value in that memory address is loaded to register. Okay. That is how you do it. Okay. That is how you do it. Right. So there's a small mistake in my, so this should be 250 because it says 250. Okay. Right. So let's do some past paper questions. In computer system paper, different years, the questions are different because the syllabus is so huge. Right? Sometimes they ask about memory address, sometimes they ask about instruction set, sometimes they ask about pipelining, sometimes they ask about stack architecture, sometimes they ask about GPR architecture. Right? So let's take a little bit older paper. Right? Do the question 20. Right. Let's do the question 21, 22, 23. So this is straight from what we discussed today. Right. So I told you this is the most important topic. So we learn everything else to understand computer architecture. So this is අපි ගැන මොකක්ද ඒකට කියන්නේ? නාට්‍යයක නම් අර උච්චස්ථානය තමයි මේ. Right. Consider machine with an instruction format from opcode RRM where R star hash is a registry address. ඔක්කොම explain කරනවා හරි because these are pseudocode. It says R hash is a registry address to specify one of the 30 registries. M is a memory address. Instructions are 32-bit long and each of the instruction format provide 5 bits for operation port. Question number 1. How large must the register address field be? කරන්න බලන්න. දැන් තේරුණාද නැද්ද කියලා හොයාගන්න පුළුවන්. තේරුණාද නැත්නම් තේරුණා කියලා හිතාගෙන ඉතින් තේරෙලා නැද්ද? Remember, at the end, everything is binary. You think in assembly level, but in reality, the computer operates in binary level. That is what decoder is doing. Show the reality to the process computer control unit. So at the very last moment, we get the reality because until that moment, as humans, we don't want to look at 1 zeros. At least we want to look at assembly code. At least read and see whether you understand the question. So I told you if you want to do IT, computer science, you must be a serious person. You must prove that you are a professional. You are a serious professional, like a doctor, engineer. So everyone can't be a doctor, right? That means everyone can't get into that seriousness, that professionalism. Because some people are not that serious in their life. we can give them only small responsibilities. Not asking that guy to do a bypass operation. Not ask that guy to help designing a aeroplane or dam or software. I don't mind you don't do this question, but try to understand as much as possible and see some solution at least. So this is partially related to what we discussed today. Other part is related to memory addressing that we discussed last week. Logical memory address, physical memory address, how the memory is organized. Right. Consider the machine with the instruction format of the form of code, operation code. Then you have three operands. First one is a registry address. Second one is a registry address. Okay. And third one is memory address. Because it says R is a registry address. It is one of the 30 registries. So there are 30 registries. Say R1 to R30. Usually it is R0 to R289. But for the simplicity, I just call it 1 to 30. And of course, we have the memory. Of course, memory will be huge. Okay. Right. For the that's it. Instructions are 32 bits long. So this instruction is 32-bit long. So I ask you to just visualize it, right? Put it into your own world, which should be pictorial because you are a human. Each of the instruction format provide 5 bits for opcode. So 5 bit is for operation code. So then the rest of the bits are for registry memory. Of course, these must be the equal size because registry address. Right. So the question one, how large must the register address field be? Remember at the end, because these guys talk about bits. So now this you are referring to the binary level code after converting your assembly code into binary level machine code. So how do you decide what is the registry address field size? So remember this is registry address because it clearly say R is a registry address, not a value. So you have if you have 30 different registries, you need to give a unique number to this because for compute everything is a number. So how many bits you need to give unique number to one of the 30 value registries? If I have 1 bit, I can give two numbers, 0 for one registry, other one 1. If I have 2 bits, 00, 01, 10, 11, 4 addresses. If I have 4 registries, I can use 2 bits to uniquely give a binary number. But we have not 2 or 4 or 8. So 3 bits, 8. 4 bit, 16. 5 bit, 32. So 16 is not enough because we have 30. So then always, but we get this number of bits. So therefore, what is the number of bits we require? So the next power of 2 after 30 is 32. So 32 is 2 to the power 5. So therefore, you need 5 bits. So then it will be 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1, altogether 32 possible patterns. So of course, 2 patterns are wasted, but what to do? Because 4 bits are not enough because then we have only 16-bit patterns. Each bit pattern must uniquely identify registry number. So therefore, because we have 30 registries, 2 to the power 5 is 32. 32 is the the next bigger value than 30. So therefore, we need 5 bits. 5 bits. Of course, if this is 5 bit, this is also 5 bit because that is also registry address. You are not referring to a different computer. Okay. So therefore, answer is 5 bits. Because you have 30 registries. 2 to the power 5 is 32. You need to give a binary number uniquely identifying the registry. 5 zeros to 5 ones. Of course, 2-bit patterns are best. What to do? So the answer is 5 bits, 21. Answer is B. Correct. Answer is B. Right. Do this 22nd one related to the same previous question. How large must the memory address field be? Right. Do it. How large must the memory address field be? Remember registry address, memory address. What is the width of this? Anyone? So if you have at least common sense, you need nothing but common sense to answer. Within 10 seconds, you can give me the answer if you have common sense. Nothing else. Just the common sense. සියල්ල කියන්නේ මොකද්ද? කොටසක් කියන්නේ මොකක්ද? අන්න ඒ වගේ අදහසක් තියෙනව නැති. So already the question has mentioned that operation code is 5 bit. We have already calculated registry you need 5 bits. So this is also registry. That means again you need 5 bits. So therefore so far we need 5, 5, 5, 15. And we know that full width is 32 again given. If full width is 32, already we have used 15. The rest of the stuff can be used for memory address. So 32 minus 15 is 17. So therefore, rest of the 17 bits, we can use it for memory address. Okay. So the answer must be 17 bits. 22 D. Yes, answer is D. Okay. Is 23 also related to this? Yes, 23 is also related to this. And 23rd question. Suppose in the above machine, each memory location can hold word size of 128 bits. Word size. Remember we discussed about word size? ඔය කතා දැන් ඔක්කොම කරලා තියෙනවා. ඕගොල්ලන්ගේ මේ බාගෙට උගන්නලා යවන්න හරි එහෙම උගන්නලා යවන්න බෑනේ ප්‍රොෆෙෂනල්ස්ලා. හරි බාගෙට උගන්නලා යවන්න බෑනේ ડોක්ටර් කෙනෙක්ව, ඉංජිනේර කෙනෙක්ව, IT ප්‍රොෆෙෂනල් කෙනෙක්ව. එහෙම යවනවා නම් මහා වෙන ගන්න අපරාධයක්. මොනවා හරි උගන්නලා යවන්න ඊළඟට යන අයත් මොනවා හරි කරගන්නවා ගොඩ දානවා. හරි මට පේන්න බැරි වචනයක් තමයි ගොඩ දා ගන්නවා කියන වචනේ. හරි. ගොඩ දාන්න ඕන නම් ප්‍රොෆෙෂනල්ස්ලා වෙන්න එපා. හරි. ගොඩ දාන්න ඕන නම් වෙන මගුලක් කරගන්න. යමක් හරියට කරන්න ඕන නම් ගුණාත්මකව ක්වොලිටියට කරන්න ඕන නම් ප්‍රොෆෙෂනල් ඩිග්‍රී ප්‍රෝග්‍රෑම් එක ෆලෝ කරන්න. ප්‍රොෆෙෂනල් මිනිස්සෙක් වෙන්න. ප්‍රොෆෙෂනල් කෙනෙක් වෙන්න. යන්තම් ගොඩ දානවා කියන මානසිකත්වයේ ප්‍රොෆෙෂනල් විදිහට මේක සමාජය කඩා වැටෙනවා. Right. Suppose in the above machine, each memory location can hold word size of 128. That means each memory address you can keep 128 of bits. That is what is my word size. We discussed that. Memory organization. What is the addressable capacity of this machine's memory? What is the addressable capacity? මෙයාගේ address වලින් කියන්න පුළුවන් capacity කියලා අහනවා. How do you find that? But that is a little bit tough question. Okay. But if you have done these kind of questions, actually these kind of questions repeat. It's very easy question. Now we have already found that for memory address in an instruction, because ultimate objective of your computer is execute instructions. So your instructions support only 17 bit for memory address because these are related questions. 17 bit. So that is for memory address. So that means your memory address can take only 17 bit. Right? Because this form third operand refer to memory address. So if you have only 17 bit for memory address, how many memory addresses we can create? That is why the question says addressable capacity. Address දෙන්න පුළුවන් capacity එක මේ අහන්න. So if your memory address is 17 bit, how many bit patterns you can create? Binary bit patterns, 2 to the power 17 bit patterns you can create. That's it. That is 17 zeros to 17 one. 17 ones. And the question says each location you can keep 128 bits. 128 bits means in byte. 128 divided by 8, 16 byte. Every location can keep 16 byte. Okay. So how many memory locations are possible with this address? 2 to the power 17. So each location 16 byte, but we have 2 to the power 17 such locations. So therefore, what is the addressable memory capacity? 16 byte into 2 to the power 17 locations. So this much of memory locations are available, or the capacity is available, because one location capacity is 16 byte, but we have 2 to the power 17 such, theoretically 2 to the power 17 such locations, because we have 17 bits for memory address in our instruction. So this is the answer, right? In bytes. But in the answers, you can see it's in megabytes. So megabytes mean kilo, mega. 2 to the power 10 is kilo, 2 to the power 20 is mega. So therefore, let's write 16 as 2 to the power 2, 4, 8, 16. 2 to the power 4 into 2 to the power 17. But if you want to make it mega, you need only 3, 2 to the power 3. So 3 plus 17 is 20. So therefore, it's 2 to the power 1 into 2 to the power 3 into 2 to the power 17. That is 2 into 2 to the power 20. Because 2 to the power 20 is mega. So therefore, this is byte. 2 into 2 to the power 20 byte means 2 megabyte. So your addressable memory capacity is 2 megabyte. Of course, that is not very realistic value. But if this is the instruction format, maybe a very small device, electronic device, addressable memory capacity is 2 megabyte, because 2 into 2 to the power 20 byte. Answer is B. Answer is B. Yes, answer is B. Okay. Right. So still we have not done the pipelining. Pipelining we'll do today. Speed up ratios. Right. Any questions about that? So you need to do some more past papers. Then you will see similar questions. So that will give you that confidence gradually. Okay. So now you have more than 1 month for the exams, right? Almost 2 months. So you have more than 1.5 months to understand, fill the gaps, do past papers, prepare for the exams, and get excellent results. Right? Professionals get excellent results. If you are a yantan santam person, don't be a IT professional, okay? Right. Do the 26 question. It's a theory question. Which of the following registers is used to keep track of the address of the memory location where the next instruction is located? That's a super easy question, right? I told you there are different registers in the processor. Right? General purpose registries, instruction registers, status registries, base index registry that we right now discuss. Then memory address registry, memory data registry. Program counter is another registry. So out of those, which register keep track of the location of the next instruction to locate? instruction register, status register, general purpose register, okay to general purpose registries, memory address register, there is a memory address buffer, or program count. So the answer is program count. Program count. Why? Remember, this is your instruction registry. This is your program count. Your program count value is copied to the memory address registry. So at the beginning, it has the first instructions memory address. So then that instruction is loaded to instruction registry. So then after decoding, remember this is updated. This is after decoding before executing by ALU. After decoding now, this has the next address of the next instruction. So therefore, sometimes it has current instructions address, that is during the fetch and during the decode. After decode, it has address of the next instruction. So therefore, sometimes it has the address of the current instruction. Sometimes it has the address of the next instruction. So during fetch and decode, it has the address of the current instruction. After decode, during execution, it has the address of the next instruction. So therefore, yes, sometimes the next instruction is address is also there here. So therefore, that is program count. Because other thing is all the other registries are not related to this. Program count is the one that keep track of the next instruction. So the answer must be E. Here, C. 27 is loaded with contents of the memory address pointed to by the program counter before fetching the instruction during CPU cycle. Select the most suitable answer for the block. Right. Read it very seriously. Pay attention to even the prepositions. Before, after, during. Do it. Or you must understand. You must already understood fetch decode execute cycle in general purpose register architecture to answer this. So it refer to the program counter. So that means instruction register must also be there. General purpose registries will be there. And memory address registry or memory address buffer and memory data registry or memory data buffer will be there. And of course the ALU is there. Now, and of course the decoder is there. Now this is your processor, and of course the buffer is there. This is the address bus, this is the data bus. Now read it again. Is loaded with the contents of the memory address pointed by program counter. You remember the program counter has during the fetch decode instruction of the current address of the current instruction, after decode address of the next instruction. Okay. So before fetching means now we are in the end of the execute. So now before fetching, that means now program counter has, because before fetching is after execution. Now the program counter has address of the next instruction, because after decoding, program count is already updated. Okay. So is loaded with content of the memory address pointed to by program count. So this will be loaded to this address. Okay. Question says contents of the memory address pointed to by program count. Right. Content of the memory address. So content of the memory address must be data, right? Little bit confusing. Okay. Before fetching the instruction during this, but it says before fetching. I think the wordings are not very clear. It says select the most suitable. So definitely not status registry, transformation, instruction registry, cache memory, and so on. Okay. But it looks like then it's not general purpose registry also. Because one possible answer is this value is here, but memory address registry is not there. So that is one possible answer, but that answer is not there. Another possibility is because it says content of the memory address, right? Content of the memory address because this is the memory address itself. So therefore, either it must be memory data registry or it must be instruction registry because content of this address will be initially here, afterwards here, right? Initially this value will be here. Then the content of this value or content of this value will be here and then here. So therefore, I'm looking for the memory data registry or instruction registry because that is where the content of this later on. So memory data registry is also not there. Memory data registry or the memory data buffer is not there. But instruction registry is there because after going through this cycle, content of the program counter will be in the instruction registry in the next cycle. So therefore, it says most suitable. So the most suitable what I can think is general purpose registry. Of course, it may go to the cache memory, but that is afterwards. That is afterwards. Okay. But there's a possibility of that is in the cache memory as well later on. Because recently access data can be put it into the cache. So therefore, this is also possible answer for me. Okay. And this is also possible answer because data can be here, data can be here, and also that, sorry, not data, that value can be here, that value can be here, and after the execution, that value can be in the cache memory as well. Okay. But it says before fetching the instruction during CPU cycle. That is value, right? Loaded with the contents of the memory address pointed to by program counter before. That is make fetch කරන්න කලින් මෙතන තිබිච්ච value එක කියලා මේ කියන්නේ මේ ලියපු විදිය එච්චර හොඳ නැහැ. හරි දැන් ඒක හන්ද මේකට එක එක උත්තර පේනවා බලන විදියට. හැබැයි ඔය වෙන්න පුළුවන් උත්තර වල තියෙන්න පුළුවන් මේක cache. හරි cache කියන එකට indirect answer එකක්. හරි cache කියන එක indirect answer එකක්. මේ දෙක තමයි ටිකක් direct answers. By the way, we have the instruction register because that will be having the data after cycle, but it can be also in the cache also, but not in general purpose registries because it talk about the instructions, not data. So therefore, I'll take this out, take this out, take this out. So the two possibilities are C and D. If I'm looking for the direct answer, instruction registry, but indirect answer, cache memory is also there. Okay. I don't know which one examiner will take because there are already 3 wrong answers. If I want to take a bit of risk, I will mark both. If I don't want to take risk, I will mark only this. But if I want to reduce the risk, I will mark this also because then I know that I will lose only 1/4 because then there will be 4 wrong answers. Okay. Right. So is it C or both CD? 27. So examiner has taken only C. That means examiner has has not thought about putting this into the cache. But that is also almost all the time happens. But examiner has only looked for the direct. Of course, this is also not very direct because this is copied to this, that is can come to here and come to here. That is why I thought because this is mentioned, maybe this is also answer, but examiner has not thought beyond a processor. Okay, but anyway, the wordings are a little bit confusing. Okay. Right, let's see whether this question has a better wording. Which of the following devices are loaded with the contents of the data, instruction, or memory address during the execution of the CPU cycle? Okay, loaded with contents of data, instruction, or memory address during the execution of the CPU cycle. What is it? program counter, control unit, instruction register, cache memory, general purpose register. So now this is very confusing. Contents of the data will be in the general purpose registries. Definitely. Instruction will be in the instruction registry. The memory addresses will be definitely in program counter, the next instructions memory address. Okay. And at the same time, these can be in cache memory as well. But again, I'm not very sure whether the examiner is looking for the indirect answer. But definitely not the control unit, right? Control unit is not keeping those things. Okay. So I'll go for A. I hope that this is O. Contents of the data O instruction O. O කියලා තියෙනවා කියලා තමයි multiple answers වලට යන්නේ. Therefore I'll go for A, C, E, and of course because the previous one examiner did not take cache memory, but in the exams of course you don't have that kind of visibility. But now I have that kind of visibility, therefore maybe I will not go for cache memory. Okay, හැබැයි the exam එකට ගියාම කොහොමද මේකත් ගහලා තමයි එන්නේ. මොකද කලින් ඒ cache memory ගත්තේ නැති හන්ද මම මේක නොගෙන ඉන්නේ. So I'll go for A, C and E. That is 28. A, C, D and E. ඔන්න D තරම්. ඒ පාර cache අරන් තියෙනවා. මොන මං නොගා හිටිය බයට cache උත් අරන්. මොකද cache එකේ තියෙන්න පුළුවන්. So especially your instruction and data can be in the cache. Okay. ඇත්තටම instruction වලට වඩා cache එකේ තියාගන්න data. data තමයි ගොඩක් cache කරගන්නේ. instructions ගොඩක් cache කරන අඩුයි. තමයි මෙතන cache නොගත්තේ ඒක හන්ද වෙන්න පුළුවන්. මොකද මෙයා කතා කරන්නේ instruction එකක් හන්ද. instruction එකක් හන්ද වෙන්න පුළුවන්. But this is data because data is heavily cache. Okay, heavily cache. Okay. Right. Which of the following devices is partially visible to the users and loaded with the contents of the data pointed to the arithmetic and logical unit? මේ පේපර් එකේ ඉතාලම අමාරු පේපර් එකක් අතරම හරි මම දන්නේ මේ 2019 පේපර් එක හරි දැන් පේපර් එක ඔච්චර අමාරුට අහන්නේ නැහැ හැබැයි මේක ටිකක් ෆාසි ක්වෙස්චන් එකක් හරි which of the following devices is partially visible to users maybe partially visible means maybe only for programmers and loaded with the contents of the data pointed to the ALU. So this is ALU. This is registries. And then you have the decoder, instruction registry, program counter, the two buffers, and so on. Now again read the question. Which of the following devices is partially visible to users and loaded with the contents of the data pointed to the arithmetic and logic unit? So data pointed to the ALU. So I'm not very sure what is mean by data pointed to ALU. Maybe what the examiner mean is data taken by ALU. Data ගන්නේ නම් එයා data කියලා තියෙනවා එයා data. Then it can't be instruction registry or program counter because those have nothing to do with the data. So this data pointed to ALU. So then data is more general purpose registry stuff. Right? Or indirectly data, memory data buffer. But anyway, memory data buffer is not there. Not the status register because it is not data. Not the transaction local site buffer. Instruction register is more related to the instruction of the data. Cache memory, partially visible to the user. Usually we are not, cache is not visible to us at all. Because even in assembly code, you don't refer to cache memory, but we refer to registries. So therefore cache memory here, we have no visibility about cache. General purpose registry is also not for data. That is the issue. Okay. So in that case, sort of nothing is correct. loaded with the contents of the data pointed to ALU. Maybe, yeah, general purpose registry is there, right? Yes, so general purpose registry has the data. And of course, it is partially visible because assembly code you can refer to registries. Of course, here the users means programmers are also users of the computer. Because the question refer to data, right? I'll go for general purpose registry because you take data from GPR, the modern computers. Right. මම අනිත් ටික අයින් කරේ ඒවා relate වෙන්නේ program එකට සම්බන්ධව. හරි. Instruction registry, status registry වගේ දේවල්. Cache memory is sort of a indirect thing. මොකද එයා refer කරනව නෙමෙයි because ALU can't refer to the cache. ALU can refer to the general purpose registry. So therefore I'll go for it. Yes, answer is C. Anyway, this is set of difficult questions, okay? Right, so 31, it's directly related to what we discussed today. Data storage used to store data to compensate for difference in speed at which the different unit can handle data is that. I already mentioned this in the morning session. How do you call this? Data storage. Data storage to store data to compensate for difference in speed at which the different units can handle data. එක එක units එක එක වේගයෙන් වැඩ කරනකොට අපිට ඒ දෙන්නට වැඩේ කරගෙන යන්න මොකක්ද අහන පාවිච්චි කරන්න ඕන දේ. ඒවට අපි කියව මොනවාද? Buffers. So that is why you have the memory address buffer, memory data buffer, because processor and memory operate in two different speeds. So when two components operate at two different speeds, we need buffers. Like E. Let's see. And so let's take another paper. This is my memory address question. Right. Do the question 22, 23, 24, and 25. Right. So let's do the question 22, 23, 24, and 25. A two-word instruction is stored in memory address 500 and 501. Say memory address 500, 501. So both addresses, the same instruction is there. Maybe instruction is too long for one location. Instruction is load $R1. So in these two locations, you have instruction load at the assembly level $R1,000. The contents of the memory addresses 1,000. So there are further memory addresses somewhere here. 1,000, 1,100. That is another address. 1,200 and 1,300. Are 1,200. That is here. You have 1,200. In 1,100, we have 1,400, 1,500, and 2,000 respectively. So these memory addresses have these values. Okay. The content of the index or the base registry is 300. So the index registry says 300. What is the value loaded to registry $R1? After execution of the instruction, if the addressing mode is immediate. So remember, if the addressing mode is immediate, this is the content. So therefore, this is a super easy question, right? So if the addressing mode is immediate, so that means 1,000, the value 1,000 is loaded to registry 1. Answer is C. 22 answer is C. So this is 2018. Question number 22. Answer is A. 23. What is the value loaded into register $R1 after execution of the instruction if the addressing mode is direct? If addressing mode is direct, so this is the memory address. So you go to the 1000 memory address and load it to the register 1. So 1000 memory address, you have 1200. So therefore value loaded for register 1 will be 1200. So the 23 answer is B. Yes, B. 24. What is the value loaded into register $R1 after execution of the instruction if the addressing mode is indirect? So if the addressing mode is indirect, so you go to the 1000 memory address and that is where your real address is. So the actual address is 1200 and then you go to 1200 and get the data to the register 1. 1200 we have 1500. So therefore value loaded to register is 1500. Okay, if it is indirect. So answer must be D. D. 25. What is the value loaded into register 1 after execution of the instruction if the addressing mode is base? If it is base, it's same as indirect, but you need to add the value. Add the value in the base, so in the index registry. So when you add the value, 1000 plus 300 is 1300. Then go and get the data from there. 1300 data is 2000. So therefore the value loaded to register 1 is 2000. Okay, 2000. So 25 answer must be E. Yes, right. So that is very simple. I told you all the details should be given. So let's move on to question 19. If any word size 32-bit in memory space can be addressed using 28-bit memory address, and each location holds one word, what should be the size of the memory space? That is addressable memory space. Right. I gave you enough time. Now this is independent question. So this has nothing to do with this question. Okay. If any word size 32 bits in memory space can be addressed. So this is how your memory looks. Read the question, right? Maybe if you are doing this course in English for the first time, this is your first exam in English medium. So that is why you need to take extra precautions, extra effort. Don't think that the life is same. Sometimes it will take a bit of more time to understand. What is the answer? So every time I read a question, I put it into my word, my world. My world is graphical, full of pictures, because I am a human. Anyone got the answer? If any word of size 32 bits in a memory space can be addressed, so that means in the memory space, it can keep word. That is basically word size. Word of size 32 means word size is 32 bit. can be addressed by using 28-bit memory address. So memory address is 28-bit. That means you can create 2 to the power 28 different addresses because 28-bit means 28 zeros to 28 ones. And each location holds one word. Of course, one word is 32-bit. What should be the size of the memory space? So that is addressable memory size. So each location you can keep 32-bit. That means 4 byte. 4 byte. So each location you can keep 4 byte and you can keep 2 to the power 28 such addresses because addresses are available. So that is the addressable memory space. And again, you can see answers are in mega and giga. So 28, remember 2 to the power 10 is kilo, 2 to the power 20 is mega, 2 to the power 30 is giga. If you write 4 as 2 to the power 2 into 2 to the power 28, that is 2 to the power 30, that is 1 GB. Addressable memory space is 1 GB. I'll go for C. 19. Yes, C. Any questions? Anything not clear? Now you can see that some of the questions are now more familiar to you because you have done such questions. That is why you need to do a lot of past papers. Right. So if every time you do another question paper, you are more comfortable. You are more comfortable. If you don't do past papers and go, you are very uncomfortable in the exams. So there is a difference between passing and failing. If you have understood concepts, you are more comfortable. Okay. Which of the following registers is loaded with the content of the memory location pointed to by the program counter? එහෙනම් ඔය වගේම හුටපටයක් කිව්ව කලිනුත්. දැන් ප්‍රේරිකාවක් වගේ තමයි දීලා තියෙන්නේ. Right. Think about it and give me the answer. It looks again, the wordings are fuzzy. Which of the following registers is loaded? මේ registers වලට තමයි load වෙලා තියෙන්නේ. With the content of the memory location pointed to by program count. So remember, program counter is keeping the latter part, it keeps the address of the next instruction. So it's basically a memory address of an instruction. Which of the following registers is loaded with the contents of the memory location? මෙයාගේ memory location එකේ තියෙන contents යන්නේ කොතනද කියලා මේ අහන්නේ. මෙයාගේ memory location එකේ තියෙන contents තමයි ඊළඟ instruction එක. So that will be later in instruction register, right? But initially it will be in memory address register. මොකද මේකට ගිහිල්ලා තමයි ඕකෙන් එන්නේ. Okay. This is again intermediary, it will be in the memory data register. Sorry, memory address content will be in the memory data register and then it will be in the instruction register. මම දන්නේ දෙකම ගණීද කියලා. ඒකෙදි මට කරන්න දෙයක් නැහැ. examiner හිතන විදිය මට හිතන්න බෑනේ. But intermediary, the content of this address will be in memory data register and then it will be loaded to the instruction register. So for me, both B and C is correct. Okay, because this is also register, but ultimately it will be in the instruction register. Which of the following registers කියලා තියෙනවා හැබැයි හරි plural වලින් දීලා තියෙනවා. So not general purpose register, not status register, not memory address register, but the content ගැනයි කියන්නේ. So possibly I will go for B and C, but ultimately it will be the instruction register, right? But I will go for both B and C because intermediary, this will be having the content. And what is the examiner's answer? Examiner has taken only C. ඒ කියන්නේ අන්තිමට අපේ විතර ආරම්භ තියෙන්නේ. ඒක ගැන ඉතින් අපිට කතා කරන්න දෙයක් නැහැ. එක එක්කෙනා හිතන විදිය අපිට වෙනස් කරන්න බෑ නේද? Sometimes you will not agree with me. So let's live with it, right? ඒකත් එක්ක ජීවත් වෙමු. That is why your A plus is not 100, right? A plus එක දෙන්නේ tolerate කරන්න තමයි ඒක අඩු කරලා තියෙන්නේ නේද? එක්සැමිනත් එක්ක තියෙන ප්‍රශ්න ඇති කරගන්න නැතුව ඒ ප්‍රශ්නෙට තියෙන බෆර් එක තමයි 95ද 90ද කියන්නේ. Right. These things we did. Right. So we'll do some more questions later on. Okay. Right. So now we can proceed. Now you should have better understanding about the type of questions you get. අපිට අර හොඳ pseudo code එකක් අහුන්නේ නැහැ. pseudo code එකක් තියෙන question එකක් කරමු. Assembly code තියෙන question එක. This one looks good. Right. So let's do this one. A stack-based architecture processor executes the following set of machine instructions sequentially. So this is generated. I told you whenever you are given a assembly code, they must tell you for which processor architecture this code is generated. So it says stack-based architecture. So this code is related to stack-based. That is why you have the push, pop, and those statements. And this is your generated code, and this will be executed in the fetch, decode, execute cycle. Assume that, right? So now you put it into your world, right? Memory locations 100, 200, 300, and 400 contains the values 4, 5, 6, 0, C, 0, 1 respectively hexadecimal. Hexadecimal only thing, yeah. So these are the memory addresses. 100, actually when I say 100, it is 100 in hexadecimal. Or is it 200? I don't know whether it's hexadecimal or whatever. Let's say 100, 200, 300, 400. And values are 0, 4. These are definitely hexadecimal because you can see C and so on. 0, 5, 0, C, and 0, 1 in hexadecimals. I'm not very sure whether all are hexadecimals or only these are hexadecimals. Okay, but definitely these are hexadecimal. These are the content, these are the addresses. The stack is byte organized. Okay, that is byte by byte. The stack pointer is 00 FD. Stack pointer means top. Now the top of the stack is 00 FD. Somewhere 00 FD. Okay, so that means these addresses are also possibly hexadecimal. Okay, so your stack pointer is 00 FD. That is top of the stack. The push and pop instruction have memory operand. So that means they are referring to memory addresses. So when we say 300, it's referred to a memory address. Okay. Which of the following could be the final result B? So memory location 500 contains 0F memory. So basically, what is the final value in memory location 500? Okay, let's execute this. Push 100. So remember, these are memory addresses. So question says these are memory addresses. So therefore, push the value in 100. Memory location 100, the value is 04. Your stack has 04. Push the value in memory address 200. Now your stack has 05. Right? This is your stack pointer now. So initially stack pointer is 00 FD, okay? 00 FD. So maybe this is now 00 FD has 0, I don't know. Maybe the next one is used, so whatever, okay? Multiply. So then pop 2, multiply and push the result. Right? Pop 2, because multiplication means pop 2, multiply and push the result that we discussed last class. But remember, these are hexadecimal. So therefore, you need to multiply this in hexadecimal. ඒකට තමයි hexadecimal වලින් ඕන බේස් එකකින් එකතු කිරීම අඩු කිරීම වැඩි කිරීම බෙදීම කරේ. So let's multiply 0, 5 and 0, 4 in hexadecimal, or you need to convert this into denary, multiply and convert back to hexadecimal because your values are in hexadecimal. Okay. So what is 5 into 4 in hexadecimal? 5 into 4 is 20. ඕන hexadecimal වලින්ම කරමු. So 20 means what? 20 in hexadecimal because 5 into 4 is 20. 20 divided by 16, 1 and 4 remains. Okay, 1 and 4 remains. So remaining 4 will be here. Right, so now, and we are giving 1 to the other guy. So that is 1, 4. Well, අනිත් එකට එකක් දුන්නේ 16ක් දුන්නේ. So ඒකයි 16න් බෙදලා ඉතුරු එක්කනව තියාගන්න. So therefore now your stack has 1 and 4. Remainder is 4. So now after this line, these two are not there. Your stack has again 1 and 4 in hexadecimal. Now you push 300, content in 300, which is 0C. Push content in 400, which is 0, 1. Now multiply. Now these two are multiplied. Of course, C into 1 is hexadecimal number එකකින් වැඩි කරාමත් ඒකමනේ. So now 14 is still there. Not 14, 1, 4. Now you have, because 0C into 1 is 0C. That is after this. Okay. Then again you need to multiply. So pop 2, multiply and push 14 or 1, 4 into C. මේක එකපාරට අමාරුයි නම් හොඳම වැඩි 10 පාදයෙන් වැඩි කරලා 16 පාදයට හරවන්නේ. එහෙම කරමුනේ. Remember this 1, 4 means අපිට කාලින් ආරගේ මේක 20. This is 20. 0C means අපිට මේක 10 පාදයෙන් කරගෙන යන ඉවරයි ඇත්තටම හරි. අපි එහෙම කරගෙන යන 16 පාදයෙන් නගලන්න ඕනේ නැහැ. අපි 10 පාදයෙන් කරගෙන අන්තිමට 16 පාදයට හරවමු. I'm going to do it again. But this time I'm going to do it with base 10 because it looks easier for me. Save not order. Right. So therefore, push 100, 0, 4. Hexadecimal 0, 4 means base 10 also 0, 4. Push 200. So this is basically 0, 4 or 4. This is 5. 0C means 1 into A, B, C, 10, 11, 12. So this is basically 12. Right? So 0, 1 means again 1. This is base 10 numbers. But the base 10 when medical lazy. Right. So push 100, that means push 4 in base 10. Push 200, push 5 in base 10. Multiply, I'm only referring to base 10, but reality it will be hexadecimal, right? So now it is 20 in base 10. And then push 300, that is push 12 in base 10. Push 400, push 1 in base 10. Then multiply, 12 into 1 is 12. Then 20 and 12 will be there because pop 2, multiply and push. Then again multiply, that is 20 into 12. Pop 2, multiply and push it. So 12 into 20. Because now I'm working with the base 10. 2 into 2 is 4, 240. Now my stack has only 214 base 10. Pop it to 500. So to the memory address 500, now you pop this, but this is in the memory it will be in hexadecimal because all are hexadecimal. So therefore, what is 214 hexadecimal? 214 hexadecimal, convert into hexadecimal. Divide by 16, 1. Then 8 remains for 80. 5. Because, so let's divide it like this. 240 divided by 16. 1, 16, 80, 5, 80. Right, nothing remains. Right, so then 16, 0, 15 remains. This nothing remains, okay? 15 means F. So therefore it is F0. Okay. F0. Yes. So therefore, the value pop it to memory address 500 will be F0. 500 memory location F0. So the final answer is F0. So do we have the F0 as answer? Now the පාදින් කරලා අන්තිමට තමයි hexadecimal කරන්නේ. මොකද නැත්නම් වැඩි කරන්න වෙනවනේ hexadecimal වලින්. Right. F0 is as there is an answer. Answer is C. Okay. So let's say 21. 2016, 21. 21 answer is C. Yes, answer is C. F0. Okay. Right. Any question? Someone ඒ වගේ තව question එකක් කරමු බලන්න. තියෙනවනේ. මේ අර කලින් කළා වගේ load immediate වචනෙම දීලා තියෙනවා. මේකත් ඒ වගේම question එකක්. දැන් මේක කරන්න තනියෙන් හරි. Push 100, push 200, add, push 300, add, pop 500. Okay, so මෙතනත් කියලා තියෙනවා the hexadecimal කියලා. මෙතන hexadecimal කියලා නැහැ. Maybe you can just consider it as base 10 numbers. Okay. So which of the following could be the final result? අටගල කර. දැන් ඒ වගේ දැන් equation එක කරාම ඒ වගේ question එක ආයෙත් හම්බ වෙනවා. So exam එකට ගියාම ඔක්කොම මුරුදු questions තියෙනවා. බහුතරය. I do this. First draw the memory structure. Memory location to 100 has 25, 200 has 55, and 300 has 85. Stack is byte organized and the stack pointer is 00FD. Stack pointer is 00FD කියන location එකට. ඒක ඇත්තටම අපිට ඕන වෙන්නේ නැහැ. All push and pop instructions have memory. We can make memory address in, yeah. 100 is a memory address. That is direct address mode. Anyone got the answer? Just use your common sense, your theory knowledge, your confidence. Right, push 100. So that means because it's memory operand, 100 memory location has 25, your stack has 25. Push 200. 55 is in the stack now, on top of. Add, pop to add, do the operation and push it back. Let's assume these are base 10 anyway, because they have not mentioned that those are hexadecimal, right? Only the addresses they are referred to as hexadecimal, but not the content. So therefore, 55 plus 25 is these two are pop and add and push it back. Then it is 80. Then push 300. 300 content is 85. Then again add. So then I will add this, pop this, add it and push it back. 165. Okay, 165. Okay. Do they say it's hexadecimal? No, right? No, right? Because 165 is not there. That is why I'm confused. Oh, they say the results are hexadecimal, right? You can see 4A, FF. So it looks like, though the examiner has not mentioned, they say hexadecimal, sorry. So they say it's hexadecimal. Okay. Now only I show that they say hexadecimal. So therefore, my calculations are wrong. Right? So either I need to do these additions and things in hexadecimal, or better convert it to decimal and do the calculation and convert back to hexadecimal. So you can do whatever you want. Because it is additions, I can even do it at hexadecimal level. Okay. Or you can convert it to hexadecimal base 10, do the additions and get the final result again into hexadecimal. කොයි විදිහට යන අපි hexadecimal විදිහට කරනවා කලින් එක අපි decimal වලින් කරන්නේ. ඒ decimal වලින් කරේ වැඩි කිරීම ටිකක් අමාරු හන්දා එකතු කිරීම නම් hexadecimal වලින් කරන්නත් පුළුවන්. Right? So therefore let's do it like that. Right. So therefore I will do it at hexadecimal because I can add at hexadecimal. Push 100, that is 25 in hexadecimal. Push 200, that is 55 in hexadecimal. I will add these in hexadecimal because answers are in all hexadecimal. 5, 5, this is actually not 55, 5, 5 and 2, 5. 5 plus 5 is 10, 10 means A. 5 plus 2, 7, because in hexadecimal 5 plus 5 is 10, 10 can be kept in hexadecimal. So therefore now my stack has 7A. Push 300, that is 8, 5. Now again add, so I add not 85, 8, 5 and 7A. A plus 5. What is A plus 5? A, B, C, D, E, F. A is 10. So 10 plus 5 is 15. So 15 is F. So 15 I can keep in hexadecimal. So A plus 5 means again, otherwise 1, 2, 3, 4, 5 you have. Then 8 plus 7, 15. 15 is F. So therefore after this addition, these are pop and FF is back. And pop that value in the stack to 500 location. So therefore the 500 location will have FF. So this is the answer. Answer is B. 10 පාදයට හරවල කරත් කමන්නේ නැහැ. එතකොට ආයි 16 පාදයට හරවම FF කියලා එන්න ඕනේ හැබැයි. Okay, so the answer must be B. බලමු answer හරිද කියලා. This is 2015 question number 20. Answer is B. Right? Answer is B. Okay. ඒකේ තර වගේම questions තියෙනවා හදන්නයි තියෙන්නේ. දැන් ඔය ස්ටුඩන්ට්ලා අමාරුම කියන ටොපික් එක තමයි මේ කරන්නේ. අනිත් ඒවා මේ තියරි තියෙන්නේ හරි. ඒ වයින් පාස් වෙන්න පුළුවන්. ගොඩ දාන අයට ගොඩ දාගන්න ප්‍රශ්න තියෙනවා. හරි බය වෙන්න එපා. මේ ඇවිල්ලා A එකට A+ එකකට යන්න ඕන. අනාගතයේ IT field එකේ ඉන්න බලාපොරොත්තු වෙන කට්ටිය. software engineer කෙනෙක් වෙන්න, tech lead කෙනෙක් වෙන්න, data scientist කෙනෙක් වෙන්න. Right. So now we'll move on with our next topic. That is instruction set architectures. Right. So what we discussed so far is process architectures. How the physically your data is processed by your processor depending on the architecture. I told you that initially people use stack architecture, then accumulate architecture, but now we have moved into GPR, general purpose register architecture, where stack and accumulators architecture is supported for individual instruction processing. In general, we use GPR architecture. So this concept is different. This is called instruction set architecture. This is at a different abstraction level. So we look at the computer at different levels. So this is a little bit at a higher level than the physical architecture level. Okay, this is a little bit at a logical level. We can subdivide computers into two instruction set architecture supporting. Some computers support what is known as RISC architecture, or the RISC reduced instruction set architecture or computer. Some computers or some processors support CISC architecture. This is at a higher level. Okay. Complex instruction set computer architecture, CISC. But in modern computers are at physical level, it's GPR, supported by stack and accumulator. But this is now we are talking at a higher level of architecture. RISC, CISC. So most of our day-to-day computers are mostly RISC computers, or it use RISC architecture. But there are some high-end processors, like some servers, they use CISC architecture. So this is an overview of RISC versus CISC. We don't go into details because this is not computer engineering. So as the name suggests, reduce instruction set. RISC support small number of machine instructions or assembly instructions. Right. So this is a particular RISC processor called MSP 430. So these are the supported instructions. Just very basic instructions like add C, sub, okay, bit, XO, and okay. So just about maybe 20, 30 instructions are supported. This is a RISC processor supported instruction. This is one of the CISC processor called IA32 and supported instructions. You can see it's far bigger than this. If this is about 30, this supported about at least 300, 400 instructions. And while here you have just add C, here you can see even so many variations of add instructions. So these are all variations of add. Here just 2, here about 10. So likewise, so many variations are supported. So we support only simple, maybe simple add, simple subtraction, but here complex add operations. Maybe add 1 is another instruction, right? Say x equal x plus y is another instruction. But here add 1, x equal x plus y. So those are all need to be executed using add. Because simple add is there, but here some complex add is there. Maybe add 3 values together, maybe another instruction. So that you can straight away do that using that instruction. But here you need to do this by using this add simple add 2 times. Okay. So therefore complex instructions are supported here. So here complex instruction that need to be built using combination of simple instructions. Right. So because only simple instructions are supported here, your physical processor is simpler here because it need to support only simple instructions. But here your microprocessor, complex physical processor must be very complicated compared to this because physically it must support these complicated instructions. So therefore, usually these processors are high-end, more expensive. These processors are cheaper. But because complex instructions can be done in single step, these can be better performing, though the processors are more complex. Of course, the processor can be more expensive, but high performing. Here, processor is less expensive, but relatively less performing. But this is good enough for general purpose computing like our laptop, smartphones. We need to go for this only when it's a very high-end computing like servers. Okay, because we need processing power. At the same time, they are very expensive. Right. So now look at the comparison. And of course, other than RISC and CISC, there are some alternative architectures also now, but your syllabus has not referred to those. Okay. Right. RISC supports small number of simple instructions. That is why we call it RISC reduced instruction set computer. CISC support large number of both simple and complex instructions. So that is why we call it CISC. So because RISC instructions are simple, in single clock cycle, most of these instruction, particular one instruction can be executed. But when you execute some of the CISC instructions, because they are so complicated, sometimes multiple clock instructions are required to execute one instruction, one such complex instruction. Because RISC support only simple instructions, we can go for fixed size instructions because they are only simple. But here some instructions are small, some instructions are long. So therefore better go for variable size instructions. Otherwise, we are wasting time, resources, because different size instructions are there. So here larger code size, because for complex instructions, you need to add multiple, your assembly code will have so many simple code. But here, maybe 4 code can be combined into one code because that instruction is available in your CISC processor. So therefore, code size is less. That means you need less memory here, more memory here. Here, processor is simple. Here, processor is complex. Here, more memory required. Here, less memory required. Here, in general, fast. Here, in general, small. Here, in general, processor is high end, expensive. Here, processor is relatively simple and cheap. This is more suitable for general programming, computing. This is more for the high-end computing. Okay. Right. So this use more hardwired controllers. This use more microprogram controllers because your complex instructions sometimes need to be pre-processed by your firmware. So this emphasis on hardware and firmware because complex, but this emphasis on more software to optimize performance. So here complexity is more handled at microprograms and hardware. But here complexity must be handled by compilers. Compilers must try to optimize your code at software level because your processor is not very optimized for very complicated hardware. And then this is more pipeline friendly. This is not pipeline friendly, but anyway, it is more high performing because of the hardware support. So one of our next topic is pipelining. So pipelining is a process optimization technique to make it faster. But in order to do pipelining, you need simple fixed length instructions. So simple fixed instructions are in RISC. So therefore, though RISC is not at hardware level optimized because it doesn't support very complicated instructions, still we can optimize it using the concept called pipelining at control level, because instructions are fixed. Because one of the prerequisite for pipelining is you need fixed length instructions. So you get fixed length instruction because it supports only simple instructions. Okay. So again, if you feel like this is so difficult, so just natural. So I told you, people say it is not rocket science. Actually, people should say it is not computer science because the most complicated device man has ever made is microprocessor. The microprocessor ගැන කතා කරනකොට අමාරුයි කියලා හිතෙන්නේ නැත්නම් ඒක මහා ලෝකේ තියෙන ඊළඟ පුදුමේ වෙන්න බෑ. ඉතින් මේක අමාරුයි කියලා හිතෙන එක සාධාරණයි. එහෙම වෙන්න ඕනේ. එහෙම නොසිතෙනවා නම් තමයි ඔයා ජීනියස් කෙනෙක් වෙන්න ඕනේ. හැබැයි අමාරුයි කියන්නේ ඉම්පොසිබල් කියන එක නෙමෙයි. මොකද මේවා හදන්නේ මිනිස්සු. ඔයත් මිනිස්සෙක්, මාත් මිනිස්සෙක්. ඔයත් මිනිස්සෙක්, මාත් මිනිස්සෙක් නම් ඉන්ටෙල් එකේ වැඩ කරන මිනිස්සෙක් මිනිස්සෙක් නම් ඌට පුළුවන් නම් අපිට කොච්චර පුළුවන් වෙන්න ඕනේ. ඌත් මිනිස්සෙක්, මාත් මිනිස්සෙක්. මොකෝ මේ දෙයියෝ හදපුවා නෙමෙයි, අමුතු ලෝකෙන් ආපුවා නෙමෙයි. අමාරුයි කියන්නේ ඉම්පොසිබල් කියන එක නෙමෙයි. අමාරුයි කියන්නේ ඔයා පොඩ්ඩක් තව සීරියස් වෙන්න ඕන. තව පොඩ්ඩක් ප්‍රොෆෙෂනල් වෙන්න ඕන. තව පොඩ්ඩක් උනන්දුවක් තියෙන්න ඕන මේක. يعني ආසාවක් තියෙන්න ඕන මේක ගැන ඉගෙන ගන්න. අපි කොහොමද මේ ඇත්ත පික්චර් එකට තාම ගියේ නැහැ. ඇත්ත පික්චර් එකට යන්නෙත් නැහැ මෙතන. අපි IT ප්‍රොෆෙෂනල්ස්ලා විදිහට මේ කම්පියුටරේ තව ටිකක් තේරුම් ගන්න තමයි සාමාන්‍යයට වඩා අපිට කොන්ෆිඩන්ස් එක තියෙනවා. නැත්නම් අපි කොහොමද ඉන්ටර්විව් එකකට යන්නේ? කෝඩ් ඇල්ලියද්දි බය වෙනව නැත්නම්. මේ සමහර ෆයිනල් ඉයර් ප්‍රොජෙක්ට් එක කරන්න වාඩි වෙන්නත් බෑ. හරි. පස්ස පැත්ත ගිනි ගන්නවා. ඇයි? එයාට සැකයි මේ මොකද්ද මේ කරන්නේ? මොකද්ද කම්පියුටරයක් කියන්නේ? මොකද්ද මම මේ කරන්න යන්නේ කියලාත් ඒගොල්ලන් සමහරවිට තේරුම් නැහැ. හරි. බබා හුකුන්ලා. තොත්ත බබාලා විදිහට තමයි BIT ඩිග්‍රී ඉවර කරගෙන තියෙන්නේ. සීරියස් වෙන්නේ නැතුව. Okay. Right. So that's it. So there are two architectures, RISC architecture, CISC architecture. RISC support only simple instructions, which can be optimized using pipelining. CISC architecture support both simple and complex instructions. So therefore, its optimizations comes from complicated processor design. So RISC is good enough for general computing. CISC is used for high-end server processing. Okay. So that level of understanding is enough because we are not doing computer engineering. Now, computer engineering කෙනෙක්ට ඔය මොනවත් අන්න බෑ. එයා ගිහිල්ලා CISC එකේ ඩිසයින් කරන්න පුළුවන් වෙනවා. ඒතර ඕගොල්ලන්ට මෙච්චර මාන්න ඒගොල්ලන්ට කොච්චර මාරු වෙන්න ඕනද? ඒගොල්ලෝ රියැලිටි එකට බහින්න බෑ නේද? දැන් ડોක්ටර් කෙනෙක්ට අපිට බෑනේ බයිපාස් එකක් කරන තියරි ගුවන්විදුලි වල ගෙදර යවන්න. එතකොට මේ මිනිස්සු කොහොමද සර්ජරි කරන්නේ? ඔපරේෂන් තියරි එකට ගිහින්. දැන් ඕගොල්ලන්ට ප්‍රොසෙසර් ඩිසයිනින් කරන්න දෙන්නේ නැහැ. IT කරන්නේ නැහැ. කම්පියුටර් සයන්ස් කරන්නේ නැහැ. ඒතකොට ඕගොල්ලන්ට පුළුවන් තියරි එක උගන්වලා ගෙදර යවන්න. දැන් ඕගොල්ලන්ට කරන්නේ තියරි උගන්වලා ගෙදර යවන්නේ. හැබැයි ප්‍රෝග්‍රෑමින් කරද්දි වෙබ් ඩෙවලොප්මන්ට් කරද්දි තියරි උගන්වලා ගෙදර යවන්න බෑ ඕගොල්ලෝ. මොකද ඕගොල්ලෝ ගිහිල්ලා IT ෆීල්ඩ් එකේ ජොබ් එකක් කරනකොට එතන කියන්න බෑ මට තියරි උගන්වලා ගෙදර යවපයි කියලා. හැබැයි එතනදි ගිහිල්ලා වැඩේට බහිනවා කෝඩින් වලට. ඩේටාබේස් වලදී කෝඩින් වලට බහිනවා. තියරි උගන්වලා ගෙදර යවන්න බෑ. මෙතනදී ආවට තියරි උගන්වලා ආය කොන්ෆිඩන්ස් එක හදලා යවලා මේව කරනවා දැන් ඔයා කියලා කෝඩ් කරා. දැන් ඔයා කියලා ඉන්ෆර්මේෂන් සිස්ටම් මේන්ටෙනන්ස් කරන්න, ඩිප්ලොයි කරන්න. ඇතුලේ තියෙන මේ වගේ කතන්දර කියලා දැනගන්න. සර්වර් එකක් එහෙම ගන්නකොට පුළුවන් නම් sys process එකක් ගන්න. Right. So now we move on to computer performance. Remember, RISC and CISC is also something to do with performance. So why people go for CISC? Because they want high performance. Right. So therefore, let's look at how do you measure performance of a computer, performance of your information system, especially performance of a computer. Okay. So the performance, the ඔයගොල්ලන්ගේ සමහරවල් performance හොඳ කට්ටිය ඉන්නවා. ඒගොල්ලෝ අවුරුදු 3න් හොඳ රිසල්ට් එකක් ඩිග්‍රිය ගන්නවා. ඒගොල්ලෝ high performing කට්ටිය. ඒගොල්ලෝ පොඩි කාලේ ඉඳලා ඒගොල්ලෝගේ අම්මලා තාත්තලා මොන්ටිසෝරි ටීචර් ඉඳලා ඒගොල්ලෝ හදලා තියෙන high performing විදියට. ඒගොල්ලෝ කාලේ කන්නේ නැහැ. කාලේ වැඩ අත ගා ඉන්නේ නැහැ. හැබැයි සමහරව high performing නැහැ. ඒගොල්ලන්ගේ ගෙදර පරිසරය අනුව අම්මා තාත්තත් හරි ලැතැජික් නේද? හරි අපි එකට කියනවා මොකද්ද? හරිම මොනවද එකට කියන වචනේ? ලාම්ක ටින්ටින් වගේ. ඉස්කෝලෙත් එහෙමයි, ඉස්කෝලේ ගුරුවරුත් එහෙමයි. එතකොට ඒගොල්ලොත් හිතනවා මේක තමයි ජීවිතේ මේ ලෙවල් එකට හැසිරුණාම ඇති කියලා. මොකද ඉස්කෝලේ ගුරුවරුත් අපිට අනිත් පැයට තියෙන ස්ලෝ මෝෂන් වගේ. වැඩක් හිමීට කළා එන ලොකු වැඩක් කියලා හිතන් ඉන්නවා. පොඩි දෙයක් කළා. හැබැයි සමහරව එහෙම නැහැ. ඒගොල්ලෝ අනිවාර්යෙන්ම අවුරුදු 3න් කරනවා. අවුරුදු දෙවෙනි අවුරුද්දට යනකොට ජොබ් එකකුත් ට්‍රේනිස් හරි මොනවා හරි ගිහිල්ලා ඉන්ටර්න්ෂිප් කරනවා. සමහරට අවුරුදු 4ක් යනකොට මිනිහා ලංකාවෙත් නැහැ කොහේ හරි ඉන්නවා වෙන තැනක. හරි. එක්කෝ ඇමරිකාවේ, කැනඩාවේ. තව කට්ටියක් ඉතින් ඕක සමහරට අවුරුදු 5කින් 6කින් යවවත් මම තාම BIT එක ෆස්ට් සෙමෙස්ටර් කරනවා කියලා කියයි. ඒක ඒගොල්ලන්ගේ ස්පීඩ් එක. So therefore we need to measure the speed. Measure the speed of computer process or computers. So the processor speed, the computer speed depends on speed of the processing and resource utilization because there can be bottleneck somewhere else. Sometimes your processor is very high speed, but you don't have enough memory. Maybe bus speed is less. Okay. So therefore we need a more comprehensive way of measuring the performance of a computer. Yes, processor speed is very important, but how do you measure it? Because performance depends on overall computer architecture, bus speeds, RAM capacity. RAM අඩු නම් කොහොමද computer slow වෙන්නේ? RAM අඩු නම් නිතරම page swapping කරනවා. virtual memory access. Even accessing of the secondary storage, like SSD. But the data gila ganne pa hard එකේ. Speed of the other peripheral devices sometimes. Sometimes even your keyboard speed. Someone key එක ගවන ටිකක් කරලා යනවා key එක වෙන්නේ. Value එක වෙන්නේ. Okay. Right. So therefore we have different performance measures. So we will look at some of those. Processor clock speed or clock rate, clock cycle time, which is pretty much related to the first one. Then cycles per instructions, instructions per second, CPI, IPS. Right. So the first one is clock speed. So that is what you refer when you buy a processor, right? You will say it's 1.8 gigahertz processor, 2.8 or 2.6 gigahertz processor. So that is clock speed. For example, I have very moderate processor in my laptop. So my processor speed is 2.8 gigahertz. So that is 2.8 into 2.8 into, this is not binary bytes, this is like kilogram, kilometers, gigahertz. So kilo means 10 to the power 3, mega means 10 to the power 6, giga means 10 to the power 9, 369. So it has 2, 8, and 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. So this is my number of clocks cycles per second. තප්පරයකට clock පදිනවා මෙච්චරක්. Clock cycle මෙච්චරක් පදිනවා. අපි මේ 0 එක මෙතනට ගමු. 0, 0, 8 to ඔන්න ඔච්චරක් පදිනවා. ඔච්චරක් කියන්නේ කොච්චරක් පදිනවද? Clock pulse. මෙහෙම pulse. මේ වගේ pulse. ගන්න මෙතන ඉඳලා මෙතනට කියලා. මේ වගේ clock pulse මෙච්චරක් පදිනවා. මෙච්චරක් කියන්නේ කොච්චරද මම කියාගන්න බැරුව ඉන්නේ. This is million, right? මේ මිලියන නෑ මෙච්චරක් මිලියන යන්නේ. ඒ කියන්නේ මෙච්චර බිලියන 2.8ක වේදවා දෙනවා. තප්පරයකට. දැන් මට තේරෙනවානේ මයික්‍රෝප්‍රොසෙසර් හදන්නේ බොහොම සුළු පිරිසයි නේද? Intel එක, AMD, Motorola. ඒගොල්ලන් මෙච්චර pulse speed එකක් ගහලත් අපිට හිතන මදි කියලා speed එක. සමහර කෙනෙක් නෑ i7, i5 මදි i7 වලට යනවා. So that is anyway that's a good measure, right? Higher the clock pulse rate, in general, faster the processing because it can process more and more instructions. Okay, more and more instructions. Because let's assume one instruction in one clock cycle. So twice the processor speed. Of course, you don't get twice the speed, but it improves because your processing doesn't only depends on the microprocessor speed. Okay, so many other factors. But in general, higher the clock rate, higher the speed. But twice the clock rate doesn't mean that twice your computer processing speed, right? Hardware වලින් ඒ උනාට වඩා ඇඟට දැනෙන්නේ නැහැ ඇත්තට සමහරවල්ලාට. But this is a good measure. Okay. Right. Next one is clock cycle time. Actually, clock cycle time is another way of telling clock rate. So clock rate is given in hertz. These days, of course, gigahertz. The clock cycle time is the time for one cycle. Therefore, this is the same measure, but give it in different point of view. Because clock cycle time is time for one cycle. Okay. Time for one cycle like this. It is 1 over clock rate. Right? So therefore, if let's assume your clock rate is 1 hertz. 1 hertz means 1 cycle per second. So then your clock rate is 1 second. If your clock rate is 2 gigahertz, again, cycle. So then what is the clock cycle time? තප්පරයට දෙකක් වදිනවා නම් එක cycle එකකට වදින්න තප්පර භාගයයි. half a second. So you can see higher the clock speed, lesser the clock cycle time. So if it is 100 hertz, තප්පරයට cycle 100ක් වදිනවා. Then what is the clock cycle time? 1/100 second. තප්පරයට cycle 100ක් වදිනවා නම් එක cycle එකකට වදින්න යන්නේ තප්පර 100යි. Now you should feed it, okay? So therefore, say my processor is 1 gigahertz clock rate. So then what is the clock cycle time? 1/1 into 10 to the power. So hertz means, gigahertz means kilo mega giga, 10 to the power 369. So a clock for one clock cycle, the time is 1 into 10 to the power 9 minus 9 seconds. 10 to the power minus 9 can the milli is 10 to the power minus 3, micro is 10 to the power minus 6, nano is 10 to the power minus 9. So that means 1 nanoseconds. So if my processor speed is 1 gigahertz, clock cycle time is 1 nanosecond. So remember, kilo mega giga 369 in base 10. On the other side, minus 3 is milli, minus 6 is micro, minus 9 is nano. So therefore, 1 nanosecond is the clock cycle time. දැන් අපි කතා කරන්නේ 10 පාදයෙන් මොකද මේ බයිට් නෙමෙයි. බිට් වලට ගියත් අපි කතා කරන්නේ 10 පාදයෙන් තමයි. හරි 1000 බිට් තමයි 1 කිලෝ බිට් වෙන්නේ. බයිට් වලට ගියාම විතරයි දෙකේ පාදයෙන් යන්නේ. 2 to the power 10, 2 to the power 20, 2 to the power 30. මේ හරියට දැනන් ඉන්න ඕන. හරි. හරියට ඉගෙන ගන්න ඕන ඉගෙන ගන්න. Nice. So that this you can do because I did similar examples. Right. So the next one is next measure. Because your computer processing speed doesn't only depends on the clock speed. There are so many other factors like architecture, bus speeds, RAM, secondary storage, access time, and so on. Right. So CPU execution time for a program. So again, this measure is also pretty much assuming that your program execution depends on the clock speed. Nothing else. Okay, තාමත් අපි එහෙම තමයි හිතන්නේ. මේ measures වල. Assume that your processing depends only on clock speeds and number of instructions and blah blah blah. Okay, nothing else. No bottleneck. This is a very ideal scenario still. So then CPU execution time, CPU එකට execute කරන්න යන වෙලාව වෙන්නේ කීයද? Number of CPU clock cycles required into cycle time. So if you know to execute your instruction program, you need 1000 clock cycles. And you know what is the time for one clock cycle. That is 1 over clock rate. So then you can say how many time you need from the CPU time. Again, assuming it is ideal. No context switching, no other bottleneck. Your operating system is not taking time for its tasks. Other programs are not taking time. Only this program is running, nothing else, and your processor is 100% concentrate on your program. So therefore, this is a hypothetical situation. But if in that kind of situations, the CPU execution time required for program is number of CPU clock cycles required. Let's assume that your program has 1000 machine codes. And every machine code can be executed in 1 clock cycle, assume. Every instruction can be executed in 1 clock cycle. And there are 1000 instructions. And assume 1 clock cycle needs 1 second. Take a clock cycle like 1 second. Samanya clock cycle like nanoseconds. Okay. This is a hypothetical situation. Right? So 1 clock cycle take 1 second. 1 instruction can be executed in 1 clock cycle. We have 1000 instruction. How many seconds we stayed? 1000 seconds. මේ instruction මේ program එක තප්පර 1000න් execute වෙනවා. මොකද එක තප්පරයකට එක instruction එකක් execute කරන්න පුළුවන්. හරි. මේක instruction 1000ක් තියෙනවා. එක instruction එකක් එක clock cycle එකකින් execute වෙනවා. එහෙනම් ඉතින් තප්පර 1000න් execute වෙනවා. So therefore, now CPU execution time for this kind of a hypothetical situation is a number of CPU clock cycles required into cycle time. Okay. Or cycle time is 1 o'clock rate. 1 o'clock rate. මේ කටපාඩම් කරන්න යන්නේ නැහැ මේක ඇඟටම දැනෙන්න ඕන. ඒවා වේගයේ දුර සම්බන්ධ දේවල් කටපාඩම් කරන්නේ නැහැ. ඒවට ඇඟට දැනෙනවා වේගය කියන්නේ නේද? යුනිට් ටයිම් එකකට යන දුර කියලා. අන්න ඒ වගේ මේක තේරෙන්න ඕන. මේව කටපාඩම් කරන්න එපා. කටපාඩම් කරගෙන වැඩකුත් නැහැ. Right. So we have another measure. Cycles per instruction. Right. So this is because your program can be sometimes very complicated program. Sometimes it's a very simple program. Some programs need more processing cycles. Some programs need less processor attention. So therefore, another measure complement to your processor speed is, or the processor clock rate is CPI. So cycles per instruction. The word is self-explanatory. Cycles per instruction. එක instruction එකකට clock cycles කීයක් යයිද? ඒක depends වෙනවා processor architecture එක අනුව විශේෂයෙන්. මොකද හොඳ processor architecture තියෙනවනේ එක instruction එකට යන්නේ අඩු clock cycles ගන්න. So again, different instructions will take different number of clock cycles. But therefore, we can say average, what is the cycles per instruction for a typical program. So that is also a very good measure. Right? So usually higher the CPI, right? Or the lesser the CPI, better. Because if you can execute one instruction in small number of cycles, that is better. And so ideally, your CPI must be less. ඒ කියන්නේ එක instruction එකකට යන cycle ගන්න අඩු වෙන්න ඕන. ඊළඟට clock rate එක වැඩි වෙන්න ඕන. ඒ කියන්නේ එක cycle එකකට යන කාලය අඩු වෙන්න ඕන. එක cycle එකකට යන කාලය අඩු වෙනවා clock rate එක වැඩි වෙනවා. CPI එක අඩුයි කියන්නේ එක instruction එකකට යන cycle ගන්න අඩුයි. අන්න එතකොට තමයි computer එකේ processing එක වැඩි වෙනවා. ඔයාට effective speed එක වැඩි කියලා දැනෙනවා. ඉක්මනට process වෙන්න පටන් ගන්නවා. Okay. So therefore, if you have n number of instructions in your program, and if your CPI is given, that is cycles for one instruction, so number of clock cycles needed is CPI into n. හරිනේ? CPI කියන්නේ instruction එකකට යන cycle ගන්න. n කියන්නේ instructions ගන්න. එතකොට අපිට එනවා clock cycles කීයක් යනවද? ඊළඟ clock cycle එකට යන කාලය හොයාගන්න පුළුවන් 1 o'clock rate. එතකොට අපිට දැන් උනට කාලය හොයාගන්න පුළුවන් processor කාලය හොයාගන්න පුළුවන්. That is n into CPI. That is CPU cycles needed multiplied by time for one cycle. That is 1/r. 1 o'clock rate. ඔන්න අටේනවා CPU time එක. ඒ program එකට. ඒ program එකේ තියෙන machine instruction ගැන දන්නවනම්. Okay. So n into CPI into clock cycle time, or n into CPI divided by into 1/r, because clock cycle time is 1 o'clock rate. ඒක අපි දැන් කලින් කිව්වනේ. Clock cycle time is 1 o'clock rate. So there is another measure. So if your CPU time is less, that is better. That is better when it comes to processing. But there can be other bottlenecks, right? Memory access time, bus speeds, and so on. So this is, we are only concentrating on the processing. Okay. Right. So then we have another one. Because so far we were 100% concentrating on processing. Processor speed. ඒක මත තමයි අපි මෙච්චර කතා කරන්නේ. හැබැයි තාම අපිට අහුන්නේ නැහැ අනිත් ප්‍රශ්න. Okay. Memory speed, memory access time, bus speeds, ඒවයින් තාම delay වෙන්නේ. So that is where we need an overall measure. Overall එකක් ඕන අපිට මේ process එක ගැන විතරක් බලලා මදි. Overall computer එක මේක process කරන්න යන වේගය. නැත්නම් overall computer එකේ processing speed එක ගැන හිතනවා. ඔයා computer එක ගන්නකොට එහෙම නේද හිතන්නේ? මේ laptop එකද හොඳ අනිත් laptop එකද? මගේ වැඩේට. මම Java program එකක් ලියුවා මේ laptop එකේ compile එකෙන් තප්පරයක් යනවනේ මේ lab එකේ තප්පර 10ක් යනවනේ මම කියන්නේ මට අන්න එතනයි මට වැදගත්. හරි. මට වැදගත් අන්තිමට ඇඟට දැනෙන්න ඕන. ඔකට කියන්නේ effective efficiency එක නැත්තම් throughput එක කියලා. ඒකට හොඳ දෙයක් තමයි මේ IPS. මේක තමයි realistic one. Instructions per second. තප්පරයකට instruction කීයක් මට execute කරන්න පුළුවන්. තප්පරයකට instruction කීයක් execute කරන්න. So for that we can use clock rate divided by CPI. Because clock rate is given, cycles per instruction is given. So then that is your IPS. So that is a better measurement. Right? How many instructions? Typical instruction. Then again, it depends on your program. Some programs will have more cycles per instruction. Some programs will have less CPI. But for a computer, clock rate is fixed. But depending on the program, CPI might change. But therefore, this is also for an average program. Typical program, I can say what is IPS, if you know the CPI. Right? So this is an example. If a processor has 1 gigahertz clock rate, CPI 1.3, that is cycles per instruction. එක instruction එකකට machine instruction එකට cycle 1.3ක් යනවා කියලා හිතන්න. එහෙම 1.3ක් යන්නේ නැහැ. හරිනේ. average කරාමනේ මේ වෙන්නේ. මොකද සමහර instruction වලට යනවා 1ක්, සමහර instruction වලට යනවා 5ක්, සමහර ඒවාට 2යි. හැබැයි වැඩිපුර තියෙන සමහර එකේ වෙන්න පුළුවන්. Simple instructions. ඒකයි මේ 1.3 එන්නේ. Right. What is the IPS? Right. So this is a typical example. Okay. Right. So IPS is clock rate, that is 1 gigahertz, 1 into 10 to the power 9, kilo omega giga 369 divided by CPI. So that means instructions per second. තප්පරයට මෙයාගේ execute වෙන instruction ගාන වෙනවා මෙන්න මෙච්චර. ඒ කියන්නේ 7 6 9 2 3 0 0 0 0 0. තව දෙකක් ගියම තව හතරක් ඉතුරු වෙනවා. So මෙච්චරක් instruction process කරනවා. Machine instructions. අපි ගොඩක් කාට ඔක එන්නේ මිලියන නැත්නම් 10 6න් එන්නේ. එතකොට මේ අපි IPS එක ගොඩක් කාට කියන්නේ millions instruction per seconds කියලා. එතකොට අපිට ගන්න 769.23 MIPS කියලා. MIPS කියන්නේ මිලියන. ඒ කියන්නේ 10 6 අයින් කරනවා. So therefore this speed is 769 MIPS, 769 millions of instructions per second. Okay. For exam එකේ සමහරවිට MIPS වලින් answer එක දෙන්න පුළුවන්. එතකොට 10 අයින් කරලා ගන්න. 10 කියන්නේ මිලියනයක්. Okay, 1.6 කියන්නේ මිලියනයක්. Okay. So 1 MIPS is 1 million IPS. So therefore sometimes your answers might be in MIPS rather than IPS. Okay. Right, so this is another example. So this is one of the past paper questions, little bit older past paper. You come out to older past paper questions, I repeat karna hai. For the multi-cycle MIPS with load take 5 cycles. You can load instruction, load, store, add, sub, koi wage wani thiyenne assembly level එකේ. So if it is a load instruction, this particular computer take 5 cycles. Store instruction 4 cycles. Let's assume there's a cycle instruction called R type, branch type, jump type, and a particular program has 10% load instructions. ඒ program එකේ 10%ක් තියෙන මේ load කියන type එකේ instruction. කියන්නේ load ඒවා අයයි තියෙනවා. 20% store, 50% R, 8% branch, 2% jump, and when you add together it must be 100. What is the average CPI? එන ඉස්සෙල්ලම කරන්න ඕනේ average cycle time ගාන හොයන්න ඕනේ. Cycle කීයක් යනවද ඔයාලට average? So that is 5 into 10%. මොකද 10යි තියෙන cycle 5 ඒවා. 4 into 20%, 4 into 50%, 3 into 8%, 3 into 2%. So that is average cycles per instruction. එක instruction එකකට average යනවා 3.6ක් cycles. මොකද මේක උනේ 150ම තියෙන R type ඒවා. ඒතකොට ටිකක් මේක 4 වලට ළඟ උත්තරයක් ඇවිල්ලා තියෙන එකයි. 4 ට ළඟ උත්තරයක්. 4 ට වඩා අඩුයි. මොකද ඊළඟට වැඩිපුර තියෙනවා තියෙන්නේ load star store ඒවා. ඒවා නෑ load star store ඒවා නෙමෙයි 50% තියෙන R type that is 4. මෙතන 130ක් තියෙනවා. ඒවට නැත්නම් 4ට වැඩි වෙන්න ඕනේ නේද නැද්ද? නෑ. නේ. මේකත් 4ම නිකන් ඒකයි. මේකත් 4ම ගන්න. ඒතකොට එයා 4ට ලං වෙලා තියෙන එකයි. ඒතකොට 110ක් මෙතන ඉන්නවා. මෙතන 110ක් ඉන්නවා අඩු ඒවා. probabilistic එක. probabilistic. By the way, you can just do the calculation again. If I thought this should be little bit bigger than 4. මොකද වැඩිපුර ඉන්නේ මේ පැත්තේ. නෑ මෙයත් 4ම තමයි නේ. Anyway, just double check the answer again. Multiplication එක වරද්දලා දන්නේ නැහැ. But anyway, I got it as 3.6. So that is the CPI. On average cycles per instruction. Clock cycle කීයක් යනවද එක instruction එකට. Okay. Right. So we discuss about computer performance indicators, so the measures. So now let's see how to improve the performance. Now you must have idea that of course the clock speed is an important factor. Processor architecture is an important factor because some processors can process complex instructions as a single instruction. Then the bus speed is important. Okay. Memory, amount of memory is important. Otherwise, you need to frequently refer to the secondary storage or the virtual memory and so on. Okay. Right. How do you improve the performance? So one possibility is at the compilation time, we can improve the performance. That means we generate assembly code which is high performing. That means we have lesser number of assembly instructions and so on. Compile time optimization. So that has to be done by the compiler. Those who write the compiler try to increase the performance by generating optimized code, machine code for the assembly code. So another thing is when you buy your hardware can be optimized. Maybe you use multiple processors, your processor has multi-cores, your processor use multi-threading. Another technique is your computer use pipelining. That is again hardware and operating system must do it collaboratively. Of course, we have no control over this as a software developer. We have no control over this. Maybe we can buy a proper computer, hardware, looking at this. Of course, we don't have any control over pipeline because it is OS and hardware. But maybe we can look at the RAM and maybe if RAM is not enough, you don't need to crazily increase the RAM. But if you feel like RAM is not enough, we can increase the RAM also. And also we can go for faster secondary storage like SSD because your computer will access the secondary storage as well. Okay. But we have some control over hardware, RAM. Okay. And also maybe we can think of the architecture, whether it can do pipelining and so on. Okay. So let's look at some certain things we have better control, especially selecting hardware. Okay, selecting hardware. Yes, you have the evening session, okay, programming, okay. Right, so you have the evening session. Everyone has the evening session, okay. And we are going to do 2023 paper first. Okay, maybe the first 30 questions. And then we'll move on to the rest of the topics, okay. Right. Right, so let's look at certain aspects, hardware aspects we have the control. So one possibility is go for multi-core processors. So multi-core processor means you have physical one processor, just one processor in your processor slot. But that processor has multiple physical processors, not separate chips, the same chip, but it has multiple cores, like 2 cores, 4 cores, 8 cores, dual core, octa core, right? Hexa core, multiple cores. So these cores can do processing parallelly. This core is processing set of instructions. This core is processing another set of instructions. So that will improve your performance of your computer if you go for multi-cores. Okay. So another option is go for multi-processors. That is not your your processor has multiple cores. You have physically different multiple processors. So that means multiple processor slots are there. Each slot you fix one processor each. And maybe that processor also has multi-cores. Multi-cores. Okay. So physically different processors. So those kind of approaches used in very high-end computing, like very critical process servers and so on. That is called multi-processor, not multi-core. And your multi-processors, and each processor may be having multi-cores. Okay. Fine. So our final subtopic is pipelining. Okay, pipelining. So now it's 11:41. So we need to do pipelining and a bit of computer, how do you call it? Pipelining and some logic circuits. That is, we did only the adder, I think. We need to do the, encoder, decoder, and multiplexer. Okay, encoder, decoder, and multiplexer. Then we need to do the pipeline. Okay, right. So because we have another session in the afternoon, we'll stop at this point. So we will do those things in another session. So then your computer architecture and logic part is done. Okay, logic part is done.